Our next speaker is also joining us for the first time, Dr. Peter Dueben, Head of Earth System Modeling at the European Center for Medium-Range Weather Forecasts. Peter's research focuses on the use of machine learning, high-performance computing, and reduced numerical precision in weather and climate predictions, and he has a passion for the quantification of uncertainty of predictions for chaotic systems. In his presentation today, Machine Learning and Earth System Modeling, Peter will walk us through the evolution of climate models from the quiet revolution to the digital revolution and how now the age of AI has evolved. Please welcome Dr. Peter Dueben. Thank you.
Thanks a lot. Thanks a lot for inviting me. It's a pleasure to be here. I'm going to talk about machine learning, and I think my first slide is going to be very similar to what Björn had. Starting with a video of like how amazing we can actually represent the Earth system already right now with physical models. So these are models that are developed for the last couple of decades, basically. They're based on equations. They now have resolutions up to something like 1 kilometer globally. And as you can see, basically, this is all model data, and what you see is basically how well they represent the Earth system in principle, and how they're actually working as a digital twin, really also allowing us to make like experiments in the Earth system itself, and also to look into fields that are basically not normally seen by satellites. And I think Björn made a very similar point. So you can actually literally look into the essence of what's doing weather and climate in principle. So great success story. We have been basically developing those models for a couple of decades now. And they're very useful. They're useful for climate, but they're also useful for weather. This is kind of a chart that is showing you how the weather forecast skill of the institute where I'm working has improved over time. So the x-axis is kind of decades in time, and the different kind of colors, the different forecast lead times. And what you see is basically how the accuracy was going up over time. So whenever you hear someone saying that weather forecast is still bad, maybe, but it was worse in the past. And what we typically see is something like an improvement of forecast accuracy by 1 forecast day per decade. So this is 20 years, and you see that we went from kind of a forecast from blue color to the red color, which means that we went from a predictability horizon of 3 days to a predictability horizon of 5 days at the same quality. And this kind of increase of this improvement of scores basically comes from a lot of different things. One of them is that we have better observations. The other one is high-performance computing, that we are able to increase resolution. The other one is that we are able to make better use of observations, and obviously also because we are able to build better models. And this is normally known as a quiet revolution, basically saying like a constant investment into this field basically led to a constant improvement over time. And that's kind of, in principle, quite drastic if you wait for long enough. But if I draw now the other 20 years, in the last 20 years, basically, you see the same arrow, and we're kind of missing the 2 days improvement over time. So to some extent, this process is slowing down a little bit. Why is this? There are several reasons. One of them is, for example, also that we're now hitting the roof in HPC, in Moore's law, scalability, and these kind of things. And it's also not for the lack of trying. So I just have a list of things that we currently do to our physical model to improve the system. I'm not going to go into any detail, but you can believe me that there are very smart people looking into this on a daily basis, doing very hard work to actually improve those models. And this is actually helping a lot to improve local representativity, for example, and to kind of improve how we represent heavy precipitation and these kind of phenomena. But in the end, if you look into the forecast scores, like literally the question like how is your temperature prediction in 10 days from now, for example, evolving, I'm not quite sure whether we will get very far with those points. We will still see improvements, but we don't see the improvement at the same scale as we used to in the past. And to some extent, this is not that bad because we have a new player on the field, and Stan basically talked about this a lot. We have machine learning. And what we see right now is that you kind of have the same plot, but a different kind of time scale on the x-axis, and you see that there's a sudden jump happening on the right. And this is when the machine learning models came in. So the machine learning models actually led to a jump in the forecast scores, in the global forecast scores. So you can argue that the quiet revolution to some extent is dead right now, but it's kind of replaced by the machine learning revolution. The machine learning models are kind of years ahead in terms of the forecast quality for weather predictions, not for climate, for weather predictions, than we have for the physical models in principle. If you want to basically make like physical models that are kind of competitive with those machine learning models, you should probably kind of think about hybrid methods. And Stan mentioned, for example, nudging, so there are ways to do this. And to make this even worse, we can actually trust the predictions of machine learning models. So a lot of people were very scared at the beginning to have like a system, a forecast system that wasn't based on equations and physical knowledge. And it turns out that those machine learning models are actually very trustworthy. And they can even predict a lot of extreme events. So just an example, there was this heavy precipitation event in Dubai in April last year. And normally, there's no reason why we should trust the machine learning model there that is kind of based on root mean square error training and so on and so forth. There are a lot of reasons you can make why this prediction shouldn't work for the machine learning model, but it actually did. So we can also represent a lot of those extreme events quite well. So what are we doing with machine learning in our field? We are basically, as Stan also pointed out, we are now having operational weather forecast models, so literally global weather forecast systems running into the 15-day future. We kind of base this on a library called Anemoy that is open source if you want to get involved. We're also looking into hybrid machine learning models, in particular into a thing called nudging, where we kind of nudge the physical model towards the machine learning model for the large scales. We are doing what we call AI DOP, and the idea here is that you kind of go from observations as input to observations as output. And this is kind of the first approach that is actually kind of trying to get rid of all model data for the training in total. So that would be kind of totally independent of physical modeling. I don't know whether this is going to work, but it's an experiment. But it's definitely kind of the first approach that would then basically get rid of also the physical model information for the training data. And then finally, we're also looking into complexity. So we're also looking into kind of basically going from just the atmosphere model for the machine learning model to an Earth system model, where you also have the components like waves, ocean, sea ice, and all these kind of things inside the model. And if you wanted to do climate modeling with a machine learning model, this is obviously what you would need. You would need to represent the whole Earth system itself. So what's going to come next? Stan showed that we had a strategy for machine learning a couple of years ago, and he said that we made good predictions. I'm not actually quite sure we did, because we didn't really think at the time that you would see this AI revolution for fully data-driven models. So we were wrong in the past, and now the question is like, what's going to happen the next 5 years from now? And it seems to be a difficult question, but I think we should really kind of step back a little bit and answer the easy questions, and by this we probably will know quite well where we get in the future for the hard questions. So machine learning is really simple, in particular supervised, right? It's input, output, learning, mapping. And we also know that machine learning is extremely powerful in a context where you have basically a lot of data, which is the case for our field. So ECMWF has kind of more than an exabyte of storage of primary data for our system of sciences. So the question is like, where do we go from here? The easy questions are, do we have the right software to kind of progress? And the answer is clearly, yes, we do. So with the machine learning libraries, we have a tool at our hands that we haven't had in our community for decades, basically an easy library system to make a lot of progress. Do we have the right algorithms? And I would also say, yes, we do. So kind of Stan again showed that you have GraphCast algorithms, for example, for a lot of those models. So we know how to build good models in principle with machine learning. Do we have enough compute? Well, you never have enough compute, obviously. So whatever compute we could get, we could use. But we have enough compute to make progress. Definitely not so much on our machines that are kind of built for weather and climate, but certainly if you kind of take the bigger machines, the public machines into account, then we can make a lot of progress. But I think the fundamental questions right now is where the field is going. First of all, how many models will we need? So how many different machine learning models will we actually have in the future? And do we actually have enough data? And I told you we have enough data, but I come back to this point later. So how many models do we need? It turns out that after a lot of progress over the years, where we kind of always adapted to the latest buzzword of the community, diffusion model, LSTMs, whatnot, and we kind of always learned how to use them, at the moment, the gene pool of models is kind of going rather down than up. So we actually kind of don't see so many different architectures anymore. Representing uncertainties, representing and understanding individual components of the Earth system is extremely complex because there are so many of them. So you actually need a lot of domain expertise to understand whether your model is good or bad. And this is coming more and more so. So even if you really want to build a competitive model today, you need probably domain scientists in the room as well. It's way too complex, the Earth system, to really understand the behavior of many specific models. So we really need experts looking into a specific model configuration to really understand how good the model is. We will not trust a model that is kind of good on one side but bad on the other. So if you want to have tropical cyclone predictions and you don't really have a lot of skill anywhere else, then you would probably not trust this model. Seamlessness is still useful. This means that you build a model basically that is running on a couple of hours. If it's good there, it should probably also be good on the climate scale and the other way around. So you learn a lot across the different kind of application areas. It will become more and more expensive to kind of train leading models as the models will become larger. And all of this points to me in the direction that we only have a very small number of models in the future. So it's not that we're going to have one model for tropical cyclones and the other one for droughts, but we're actually going to have big models. And this goes in the direction of foundation models, and the model itself is basically then defined by the latent space rather than the application area. So you can have the same latent space but applied in different time scales, for example, with different time steps, but really the information content is going to be in the latent space of the models. And this is kind of something that we do in this direction. We kind of build what we call a foundation model, the weather generator. And the idea here is that you don't take just one application area, like, for example, for the AIFS, but you really have basically a tool that can digest all sorts of different data sets. This can be reanalysis data sets, it can be simulation data, it can be observations, it can be the latest, greatest of Björn's simulations with kilometer scales, and so on and so forth. And the weather generator should be able to digest all of this and then kind of apply it for a lot of different application areas as well. And our ambition to some extent is that you have a model that can work on all sorts of different resolution levels, so it can digest data at 100 kilometer resolution, but also at 100 meter. It can be global or local, and it can also kind of be applicable to past, present, and future, like a lot of different areas and regimes, if you want, in terms of the climate space. It's based on mass token learning, so self-supervised rather than supervised. And again, the size, I think we are heading towards something like 100 billion degrees of freedoms. We're nowhere near. But I think that's the ambition to also kind of, as experience shows, as you kind of have to kind of scale them up with those foundation models, we also want to do that here. And once you've done this, you have basically a latent space that you can work with, and then you can use it for different applications. So if you use satellite data or synoptic observations as input, and you spit out something that looks like reanalysis data, then you have data simulation. If you kind of use initial conditions for the weather forecast model and just kind of progress it into the future, you have a global weather forecast, and so on and so forth. I'm not going to go into detail here. It goes all the way to a state where you can just basically ask the model, like, I want to have a weather state, how it would look like in 10 years from now, or in 10 years into the past, and it will give you some sort of state that is very realistic, very similar to what Stan mentioned with Seabottle, actually. So it's also very generative in the sense that it will create a lot of information. So that's the hope. And in our project, we kind of apply it to 22 different application areas, and we want it to be basically a digital twin of a project called Destination Earth in Europe. But on the other hand, to be fair, this is all a big dream, and there's no guarantee that it's actually going to work, right? So at the moment, this is kind of, I think, one of the fundamental questions of our field. How big are these models going to be, and how much benefit do you get if you go down this road of foundation modeling? This is just to show you that there's already data, the project is 6 months old, and we already have some results, so it's not just a dream in that sense, but it's also kind of slowly getting there in terms of data. Do we have enough data? From parameterization emulation, yes. So you basically emulate parts of the model and kind of speed them up, but to some extent it's difficult to show that this is really competitive. For global weather predictions, yes, we have reanalysis data, and we can learn this. Obviously, you can always go do better. Seasonal predictions depends on the question and the approach, and I'm not going through this in all the details, basically. You will see that for the different components, for land modeling on the surface, we probably have enough data, but not so much on the deep land. For sea ice, we have enough data. For ocean, if you go to the deep ocean, you won't have any data, really. So kind of the deep ocean, no. But for the surface, yes. Global atmospheric chemistry, the quality of the data is a problem here. And then climate simulations. If you want to measure climate sensitivities, we don't have enough data for machine learned models. We need the physical model to actually kind of provide that context. If you go for tipping points, probably also not in principle. Extreme weather events in the future, you also want to kind of fill in your space with a physical model to really understand what's happening there. Downscaling, partly from observations, partly not. And then gray swans events, these are the events that really happening only once in 100 years or something like this. You also can only be sure that the model is doing the right thing if you kind of add physical model data to the training, I guess. So in general, we have a lot of application areas where machine learning will make a huge difference, and a lot of application areas where it will be difficult. And the question is, what do we do if we don't have enough data? And the answer is obviously use a physical model. So until now, you may have, you could probably think that my talk would be very different to Björn's, but it actually isn't, in a way that I still think that we need those physical models, and we need those physical models really also to kind of get the best physical realism at the small scales, and this is kind of what you get with these kilometer scale models, for example. So you need initiatives like Destination Earth, for example. The future of physical models, and I'm going to be very brief here, I'm a little bit concerned because the efforts are going to go down in physical modeling, and it's not only because machine learning will take over a lot of the tasks, but also because it will be very difficult to actually kind of really find the right compilers, hardware, software, and staff in the future to kind of build those big models. We're talking about 1 million lines of Fortran code for IFS, right? So it's going to be difficult to maintain those models. And so therefore, the point I want to make is basically, if we want to get better AI model for climate in the future, we really can't stop investing into physical modeling. We still need those physical models, and they're really kind of under pressure right now. And I think many of those physical models will actually not survive the next 10 years. For machine learning, we want to go into like open source general infrastructure because that's really helpful for the community. Put the models out there, put the libraries out there, and we're doing this successfully. We're going to have a little bit of shift of like what we concentrate on in terms of the machine learning developments. So data handling is going to go down a little bit because it's really difficult at the moment, but in the future it's probably going to be easy. Dataset generation is going to be a huge issue and a huge kind of thing where we can actually kind of produce benefits. So we need physical models to kind of do more there. Architecture development is going to become a little bit more boring. As I said, the gene pool is going down. HPC efficiency is going to be a very big topic soon in terms of we want to scale the models, but then at some point it's probably also going to be less interesting. And yeah, what the future is going to look like in terms of the whole community is also there's going to be quite a big change in a way that we will have high-resolution physical models, and we'll have observations, and these models will basically generate data sets. Then there will also be the training, like the modeling infrastructure that is provided by the bigger centers, but usable by everyone. In operational predictions, so reanalysis products and weather predictions, we will see a huge shift away from physical towards machine learning. And then if users come in, they basically will be able to kind of really use this huge portfolio of infrastructure, basically, and will use it for their own application by bringing their own data. And in the end, basically, the limit of the quality is going to be mostly around the data that they bring into the application rather than the model infrastructure itself. And this, to some extent, means that we will have less of a difference between physical models and machine learning models. So what I mean is basically there's going to be Björn's icon simulations that are going to be used for the training data sets that then WeatherGenerator is going to train from, that then a local limited area model kind of may use to kind of set boundary conditions and so on and so forth. So it's going to be more muddled up. And the same is also true for modeling and services. And also this means that there are more user groups that can actually kind of tap into the space and make use of the tools itself. So the future of Earth system modeling is going to change in a sense that so far we always develop the best possible models in a holistic sense. We really try to always kind of build the best physical models that we can do. And that's going to change into something like we're going to use physical models and observations to generate training data sets that then are going to be used by machine learning models to kind of really make the link to the impact user. And this can kind of relate to the past, present, and future in a sense that you will have tools, machine learning tools, that you can ask, I want to have a tropical cyclone prediction for 1979, and the model will give you something. So it will be very kind of flexible in the use case in principle. And again, that's a problem, actually. That's not only a benefit, but also a problem in a way that it will be very easy for domain scientists or other to kind of generate nice, glossy pictures. And it's going to be very difficult to actually understand how much actual physical information or from both observations and the modeling is going to be in those tools. So we're walking towards an era where basically everyone will be able to build and produce high-resolution, beautiful pictures. The video that I started with, everyone is going to kind of be able to do something like this in the future with machine learning tools. But it's going to be very difficult to see what when we are wrong, because the machine learning model will give you a result, whatever. For weather applications, it's easier, because we can always verify what's happened for the last year of weather, for example, so we can basically make empirical studies, but for climate, this is going to be a fairly significant problem. So it will always be very difficult to understand, like, how much of a prediction that is based on the probability distribution of your machine learning tool is actually going to be found on physics, rather than best guess and generative machine learning filling in the gaps. So, long story short, I think we will need to be very critical about this. So I think everyone in the room should always challenge in the future where a specific result is coming from, and kind of to make sure that we're not just inventing something based on machine learning and nice pictures, but actually by a physics-informed machine learning model, if you want. This is the last slide, and just kind of to mention that obviously machine learning will not stop there. Machine learning will also go further than just the modeling part. And for me, it's kind of always interesting to see how we kind of still distributing weather information. So in the past, it was via BBC radio. Now you kind of have an internet browser and a mobile app, and that's kind of giving you weather information. But I'm still sure that you will be able to actually improve on that quite significantly. And if you now look at the next generation of people looking into TikTok videos, you can probably guess that they won't be happy with our apps today. So in the future, I'm sure you will have capabilities like you make a picture, for example, and just kind of scroll through time, and the machine learning tool, underlying machine learning tool, will kind of show you how the weather is going to evolve in the next 10 days. You can also do the same with climate. You make a picture, and then you basically get climate information served that will tell you something about the extreme events in the future and stuff like this. So there's a lot of capability here with machine learning. You can even think about gaming scenarios where you kind of drive through, I don't know, a city of your choice at your birthday, like literally the birthday, and see how the weather was looking there and kind of what the different cars looked like and stuff like this. So there's a lot you can do with machine learning here. And then also for planning, like the way how weather information is going to be used, I'm sure it's going to be very different in the future. That's all I had to say. Thanks a lot.
Thank you, Dr. Dueben. We have one. Does anyone have any questions? We'll just take one question. All right? Yes.
Thank you for the presentation. It's very interesting. You mentioned about the future. It's about the client or the customer bringing their own customer data. So from your understanding or your current view, how can a company provide a new data that improves, let's say, the EC46 data better than what we have now? So what is the additional data that we can provide in order to have a better focus for
Yes.
the whole general for the EC46?
That's a very good question, because I don't think we actually know what data we will need in the future. I mean, we obviously need information from synoptic stations and satellites, whatever we have at the moment, but obviously in the future, we may be able to digest very different data sets, like coming from mobile phones or from cameras, from self-driving cars, and so on and so forth. I think the important part is that you get this data into like benchmark data sets, that we really make sure that we add those data sets to the existing big data sets already that people can play around with, and then actually extract information and play around and see how much benefit it gets. So I think my answer to your question would probably be try to add it to the existing frameworks and let users play around with it and see how much benefit it gets.
All right. Thank you, Dr. Dueben.